we kind of talked a little bit about what stoichiometry means, right? We gave kind of an overarching definition of stoichiometry. Does anyone remember what that definition was? Okay, so stoichiometry in itself is basically putting quantities to chemical reactions, right? That's kind of been our goal for this chapter. We've done a lot with mole conversions. We've done a lot with balancing reactions. And so now we're going to be able to put mole conversions and balancing reactions together, right? We're going to have a chemical reaction and we're going to be able to put quantities to it. So we're going to start talking today about something called a mole ratio. Okay, the ratio is a conversion factor that relates the amounts of moles of any two substances in a reaction. So the mole ratio allows us to compare two different chemicals or two different compounds in our reaction. Remember, we cannot compare compounds grams to grams, right? Because let's give the example again. 1 gram of hydrogen atoms would be 1 mole of hydrogen atoms. But 1 gram of oxygen atoms would be 1/16 of a mole, right? Those quantities are totally different. Although the masses are the same, the quantities of that substance are totally different. So when we compare and when we talk about moles and changing between one substance and another, it has to be done in what's called the mole ratio step. So we're going to add this part to our conversion. We're going to be able to say, go from grams of our reactant to grams of our product, right? And we're going to do that switch in the mole ratio step. Okay, so let's just look at an example here in this chemical equation. If I asked you for the mole ratio between potassium chlorate and oxygen gas, what would you tell me? What's the mole ratio between potassium chlorate and oxygen gas? Just here. What's the mole ratio? 2 to 3, right? The coefficient tells us how many moles of that substance need to be in the reaction for the reaction to work, right? For the law of conservation of mass to be satisfied, we have to have 2 moles of potassium chlorate break down to form 2 moles of potassium chloride and 3 moles of oxygen gas, right? So when we talk about mole ratio, we're looking only at the coefficients in the problem, right? That's what gives us the information for mole ratio. Okay, so ratio between potassium chlorate and potassium chloride would be 2 to 2. Okay, you can reduce them, but it doesn't save us any time. So I don't bother reducing them when we use them in problems, right? It's not saving us anything is what I'm saying, right? We still have to do the process. So reducing 2 to 2 down to 1 to 1, is it valid? Yeah, but does it do anything for us? No. Right? I think sometimes it'll confuse us more because then we don't know where the 1 came from because it should be a 2, right? So I don't think it does us anything. All right. So we're going to start looking here at how can we convert from moles of one substance to moles of another. Okay? These are the most basic stoichiometry problems that we can do, starting with moles of one of our compounds and going to moles of another compound. So the reaction is given up at the top. Do you think that reaction is balanced? Okay, the first thing we've got to look at is the reaction balanced? So are these printed on your slides for you? Okay, take a look and see, is that reaction balanced? Right? The fact that it has a coefficient in it is a good clue that it is, right? But let's check, okay? I've got 1 carbon, 2 times 2, so 4 oxygens, 1, 2, 3, 4 oxygens, 2 lithium, 2 hydrogens. So I think it's balanced, right? The fact that it has a coefficient is a good clue. If it doesn't have any coefficients in it, then we really need to check. Is it balanced or is it not? Okay? So we have to start with the balanced equation. Second thing says, how many moles of lithium hydroxide are required to react with 5 moles of carbon dioxide? So here's what we're going to do. When I do stoichiometry problems, I like to kind of zoom in or focus on what I'm working with, okay? It's giving me, my starting amount here is 5 moles of CO2. So I like to write that up at the top. That's what I've got, right? That's my starting amount, 5 moles of CO2. It says how many moles of lithium hydroxide are needed to react with 5 moles of CO2. So we want to know, if we put in 5 moles of CO2, how much lithium hydroxide is it going to take so that the reaction goes all the way to completion, right? We use up all of the CO2. So the way we do that is we do a conversion chart, okay? And we always start our chart with what we know. 5 moles of CO2. Okay, 5 moles of CO2. And in any T-chart, what goes right on the bottom here? CO2. Right? And more specifically, not what CO2? Moles of CO2, right? We have to cancel what's going there. Now, we said if we want to compare 2 different compounds, right? Our goal is to go from moles of CO2 to moles of lithium hydroxide. The only place in our chart that we can convert or we can make a switch between CO2 and LiOH is if they are both in moles. Okay? This step right here is called the mole ratio step. Okay? It's called the mole ratio step. And this is the only place in our chart where moles does not necessarily get the 1. Okay, moles does not get a 1 because here we're just proving the ratio from the reaction. And we just put in numbers that come directly from the balanced equation. And so we go to CO2 and we say, okay, well, what coefficient sits with CO2? Just a 1. From the regular reaction, just a 1. And from lithium hydroxide, what coefficient sits there? Okay, and that's it. That's my conversion, right? I've canceled moles of CO2. I'm left with moles of lithium hydroxide, which is exactly what I was searching for, right? The only time I can make the switch is if it is mole to mole, right? Mole ratio. So then I just do the math, and I say I need 10 moles of lithium hydroxide in order to react. Do you think you could have predicted that without doing the whole chart? Right? Just by looking here at the ratio, right? I need twice as much. That is nice when our numbers are pretty and whole. It makes sense, right? But when I'm given a certain number of atoms or if I'm given grams, then it gets a little stickier, right? So these conversions, a lot of the times, give you nice numbers, and it's pretty and easy to see. But I'm teaching the method so that when we get to complex numbers, it still applies. Yeah. Okay, this one requires us to balance it first. Then we'll start in with the question here. So now I'm going to come ask my question, right? 0.66 moles of hydrogen peroxide. Well, how do we know which one is hydrogen peroxide? That doesn't sound like something we know how to name. So how do I know which one's hydrogen peroxide? It's the only one I don't know, right? I know H2O and I know O2, so hydrogen peroxide's got to be the other one, right? So I'm starting with 0.66 moles of that, and it says how many moles of O2 will be produced. It does not matter if we are comparing 2 reactants like in our last problem or if we were comparing a product and a reactant. It makes no difference. We still solve the problem the same. So I'm going to start with what I know. 0.66 moles of H2O2. Right? This is why I said it's so important to keep the name of the compound and the unit in the T-chart because now it's extremely important. Right? Moles of H2O2 are going to go on the bottom. And what's going to go on the top there? What am I trying to get to? So can I go right here to grams of O2? No, I can never switch moles of one to grams of another. I couldn't go moles of one to molecules of another. I can't go grams of one to grams of another. I have to be mole to mole. So I'm going to go moles of O2. Where do I get these numbers from right here? The equation, right? Because what is this step called? Mole ratio step. Okay, so there's my mole ratio. I'm going to go pull the numbers directly from my equation. So H2O2 is going to get a 2. O2 is going to get a 1 because those are the coefficients that sit right in front of them on the chemical reaction. So that gives me 0.33 moles of O2. Right? When the numbers are nice and pretty, it makes it easy for us to be able to predict that, right? I think you guys could have predicted that without doing the chart. But that's why moles to moles is easy. Now, if we're going to go from moles to grams, we've got to include the molar mass of one of our substances or both of our substances, right? We've got to figure out what we're looking for, what we have, all that kind of stuff, okay? So, what mass in grams of glucose is produced when 6.4 moles of water reacts with carbon dioxide? Okay, so this one is going to be a little bit more difficult to predict, right? We're given moles. We want our grams. We've got to do the whole chart here, but we've got to start with balancing first. So I'm going to give you a minute or so to balance this one first. If you can do it without the list, I'm going to suggest that, okay, just to speed up the process a little bit, right? Find an easy change if you can and go from there. Oh, nope. Is that it? Yeah. 6616. Right? Without my list, I started there, right? C12 and C6 and H12. I started with those on the to transform the left side, right? And then I let my oxygens trickle down from there. Okay? So let's go start looking at our problem here. It says, when 6.4 moles of water, so I'm going to write my starting amount up in front. The reason I write them on top of the reaction is just so that I can kind of zoom in on what coefficients do I need to be paying attention to, right? I like to be able to do that. All right, so I've got 6.4 moles. It says what mass of glucose is produced. So if it asks me for mass, my unit's going to be grams here. So I'm just going to go ahead and make my question mark grams, right? I'm trying to find grams of glucose. So I'm always going to start my chart with what I know. So that's 6.4 moles of H2O. Do I need to bother with grams of H2O at all? Nope, because I'm going to go directly here to moles of H2O. And then where can I go on the top here? What do I need to be doing? I need to go moles of glucose. I need to make my switch because I want to start examining glucose. Okay, and so these numbers come directly from our chemical equation. So water is going to get a 6, right? And what's glucose going to get? A 1, right? Because our coefficient right there is a 1. Okay, but is my problem done right there? Can I stop right there? No. Okay, sorry, go ahead.
So what if you did have something that was like, if it was CO2 and H2O in this problem, if it was 6 to 6, you go 1 to 1?
You can, but it doesn't save us any. I mean, it might save you a couple seconds plugging it in your calculator. But the reason I recommend not doing that is because if I have to go back and look at a problem and I've got them reduced 1 to 1, then I'm not really sure, like, did I make a mistake? Did I reduce it? Like, it makes it clearer to me if I just leave the coefficients exactly as they are in the problem. But it's your choice. All right, if I stopped right there, it'd be in moles, but that's not what I want. I want to get rid of moles of glucose and go to grams of glucose. So you've got to find molar mass there of that compound, just like normal. And in this step of our chart, moles goes back to getting the 1. Okay, let me make this really clear. In this mole to gram step, we do not put the coefficient back with moles. Okay, I know glucose has a coefficient here of 1 anyway, but I would not go back and put the coefficient because the molar mass I'm putting in right here is only representative of 1 mole of that substance, right? Okay, so did you already calculate that? Are you way ahead of me? Sorry. Okay, what is your molar mass there? 185. Is that what you told me? 180. Thank you. Okay, so now we plug it in, multiply across the whole top, divide by the whole bottom, and we get a value of 192 grams of glucose. I can go moles to grams as long as they're the same compound. I could not go moles of water to grams of glucose, right? Because those would be 2 different compounds. The only time I can have 2 different compounds in the same column of my chart, it has to be mole to mole. Okay, does that kind of make sense? Yeah. Okay, so I can go mole to gram, but they have to be of the same compound. That's why I made it kind of a big deal that we need to carry our chemical name all the way through the chart. Right, so we know when we're making that switch or when we're not. Because if we just wrote out mole, gram, like, we're not going to know what we're talking about. Right, so keep that name all the way through. Okay. Why don't you try the next one here on your own? It's already balanced for you. It says how many grams of O2 are required to produce 3.12 moles of H2O. Right? It does not matter to us here that we're starting with a product amount and we're working backward to find a reactant amount. That does not make a difference. We still solve it exactly the same way. Right? Start here with moles of H2O. Right? And then go to find grams. So I'm going to give you a little head start and then I'll get it up here on the board. In this mole to gram section of our chart, moles goes back to getting the 1 because the grams that we're putting here is equal to 1 mole of that substance. If we were saying 32 is equal to 5 moles of O2, that wouldn't be true, right? 32 grams is how much 1 mole of that weighs. So the only place where moles doesn't get the 1 is in the mole ratio step. Otherwise, if we're going moles to grams or moles to atoms, moles goes back to getting the 1s because that's what the relationship is that we know. Right? 32 grams is equal to 1 mole of that substance. Okay? Because otherwise we're putting 5 in twice and we're canceling out the work we did with the mole ratio. Right? So we just went in there once. Okay, sorry. How many grams of water is produced if 56 grams of oxygen is combined with excess ammonia? Okay, for right now, that doesn't mean anything to us. It will in a little bit, but for right now, it just means that oxygen is going to be all used up. We're going to use up all 56 grams of oxygen in our reaction, and we're going to have a leftover of our other reactant, right? Later, that will mean more to us than it does right now, and that's okay. All right, so right now, it does not affect our problem at all, okay? We're going to start with what we know, which is 56 grams of O2. And we're going to work it all the way to get to grams of water. All right, so I'm going to go grams of O2 to moles of O2. And then what's going to be my next step there? Mole to mole, right? Mole ratio. So moles of O2 to moles of H2O. And then I'm going to keep going and go to grams of H2O. Right. I like to do the units first and then go back and put in my numbers. You can choose whatever path works best for you is fine. But I know that 1 mole of O2 weighs 32 grams. I know the mole ratio for O2 is 5 and for water is 6. And I know 1 mole of water weighs 18 grams. And so I got this value for my answer. So you can tell me if that's close to what you had or not. Whoa. Is that all the balancing that it needs?
Yeah.
1, 4, 1, 2. Okay. rational. I started with well over, right? A lot more than 1 mole. If 20 grams of HF is 1 mole, I started with 600 grams. I started with significantly more than 1 mole of my substance. I need 4 times as much as that one. I mean, our answer, if you walk it through, it makes sense. We're not getting some really, really small number or some number times 10 to the 40 something, right? Our answer fits within what our brief guidelines are. So, okay, feel simple enough?
Wait, how can you check if it makes sense?
You can just look at rough numbers here. So if I know that 1 mole of HF weighs 20 grams, I'm starting with well over 1 mole of that substance.
Okay.
Right? And so then I'm just looking at my mole ratios between these two, and I'm looking at my final answer to see, does that seem to fit? Right? Okay. It's not a set in stone thing. You're just looking to make sure. If this would have come out to be 0.24 grams, I would have think that should be a red flag. Right? I'm starting with 600 grams of one. I'm ending up with 0.24 grams. That doesn't seem to fit in my picture. Right? That's about it. All right, I'm going to skip over the next couple and go to our last really version of stoichiometry calculations, and that's when we go molecule to molecule. Can we envision how molecule to molecule is easier than gram to gram?
Because it's just Avogadro's.
You don't have to calculate molar mass. You just have Avogadro's number. And if we go molecule to molecule, you've got Avogadro's number on both sides of your equation, both sides of your T-chart, right? Top and bottom. So that's going to make it a lot simpler. So let's just see what we can do with that. Okay? We already did this reaction, so let's just go back to what it was balanced at. 4 and 2, is that right? Mm-hmm. 1, 4, 1, 2. Okay, so if I start with 1.21 times 10 to the 24th molecules of tin, how many hydrogen molecules are formed? So we're looking for the number of molecules. And I'm starting with 1.21 times 10 to the 24th. Okay, so I'm going to start with what I know. I'm going to convert from molecules of SN to moles of SN. Then I'm going to do my mole ratio. Then I'm going to go moles of H2 to molecules of H2. So now if I pay attention here, right, moles still gets the 1. And how many molecules are in 1 mole of anything?
6.02.
Right, Avogadro's number, worth, right? And so then here's my mole ratio step. 10 gets a 1 and H2 gets a 2. And then Avogadro's number is there again on the top. Now, do you see how Avogadro's number is in both the numerator and the denominator? So do I need to bother plugging that into my calculator? No, right? All I'm doing is taking my starting amount times 2, right? And then I divide by whatever's on the bottom. So it's just going to be a bunch of 1s. So that gives me 2.42 times 10 to the 24th molecules of H2. What if in this problem it had asked me to solve for not molecules of H2, but grams of H2? The only thing that would have changed is the last part of my T-chart. I would have went 2 grams, right? That's it. So you can mix and match what they're asking for here, right? You can mix and match and solve any calculation. Now you know how to do any of these. You can go with whatever you are presented with, right? You should be able to calculate whatever you're presented with now because you know how to do every type of calculation. Now you can go work through all of them. Okay?